So we're going to be learning about Conway tangles or rational tangles and continued fractions. Okay, so first of all, so what is a tangle and what is a rational tangle? So basically, a tangle is just an embedding of two intervals into a ball sphere pair. So the tangle is a proper embedding well, we can also add a bunch of circles, but it's essentially this. It's a proper embedding of a disjoint union of two intervals and a bunch of S1s into a ball sphere pair, like this. So let's draw a picture. We've got a sphere here, and then we might have something that looks maybe like this. Maybe this crosses over, and maybe we've got an additional S1 that has been embedded into this. So this is an example of a tangle. And so a proper embedding, recall that this just means that we're attaching the endpoints of the intervals to the boundary of the ball. Right, and so we can sort of think of this as a generalization of a link. So another thing that we might want to do is that we have a link like this, and now a tangle, we can equivalently think of this as just considering a part of this link diagram, like a disk, where we have four strands crossing out of the boundary. So it's basically just sort of localized picture of a link. And yeah, so these are kind of equivalent, so we'll think of both of them. But yeah. So this is another notion of a tangle. So what is a rational tangle? Well, okay, I'll get to this in a moment. So first of all, we'll say what we mean by tangles being equivalent. And this is, well, we consider two tangles to be equivalent if there's an ambient isotopy between them. So in particular, if we adopt this link diagram perspective, then this means that we can get from two tangles, from one tangle to another, by using the Reidemeister moves. So these are basically resolving this one to this. So this is the first Reidemeister move, I think, and then we've also got this, we can pull strands apart. And then the final one is doing this thing where we can push this arc over a crossing, or push this strand over a crossing. Right, and so a rational tangle. So what is a rational tangle? So it's a particular type of tangle so we can obtain it in a particularly simple way. So when we consider rational tangles, we won't consider any additional embedded circles. And the way we get this is by a bunch of twists. So we have certain moves. And let's make this precise. So let's say we have a tangle diagram here. So we can use some sort of geographic notation. So this is northwest, this is northeast, this is southeast, and this is southwest. So the core idea is really simple. The idea is essentially we're allowed to take one of this, like the southwestern strand, and cross over the southeastern strand, or we could do this swapping the southeast and northeast strand. We could also swap these, swapping any strands basically. And there's a simple notion of how to build this. So first of all, I just define some twists. So definition. So we define a horizontal twist. So first I'm just going to define T1. This is obtained as follows. So we have some sort of a tangle here, and then we're taking the southeastern strand and crossing it over. So this is our tangle diagram. So this is applying T1 to the tangle B. We don't need to do this only once, so we have the additional notion of a horizontal twist TA, where A is any integer. This just means that we've twisted it around A times. So if A is negative, then in particular this crossing will be in the other direction. And now we also have the vertical twists, and this is essentially the same thing. Well, it's not the same thing, but it's the same idea. Vertical twists, which we will denote by a prime, so T prime of A, where instead of doing the swap here, then we're doing the swap down here, and so so this would be T prime 1, and if we want, we can twist around several times. So if we get something like this, this would be T prime 2. And so this is, these are horizontal twists, and so this is a vertical twist, and the previous one was a horizontal twist. And now, essentially, a rational tangle is just a sequential, what we get from like sequentially applying vertical and horizontal twists. We just alternate between them, and we start with either this picture, which is called, so this is called the infinity tangle, and we can also have the so-called zero tangle. This is a zero tangle. And then we have two different sort of approaches that we can take, but let me make this precise. Right, let me just erase the board. Okay. Cool. So, yes. So we define a basic rational tangle as follows. So we're using one of the two procedures. So the first procedure that we can do is to start with the zero tangle, and apply. So first we do a horizontal twist, TA1, and then T prime A2, t a3, t prime a4, and then so on. And then we stop at some point. The other allowed procedure is instead starting with an infinity tangle and apply. So now we're going to do it kind of shifted. So instead we're going to do t prime a1, t a2, t prime a3, and so on. And again, we stop at some point. And so this is called the basic rational tangle. And yeah, and so note that we've applied all of these moves from the right here, or the bottom. Now, in general, when we're defining a rational tangle, we can apply these, we're allowed to apply these also from the left or from the top. But it turns out that this won't really matter. So in particular, if we add a twist on the right, we get something that's ambient isotopic to applying a twist on the left. And the same for north and south. So we're gonna sort of simplify things by only considering basic tangles. And so if we wish, we can define some algebraic structure on tangles by saying that we can add two tangles. So here's a tangle A, and here's a tangle B. And we can add them by pasting them horizontally. And then we also have the plus prime notion, where we paste them vertically instead. So this will give us a new tangle, and it will also give us a new rational tangle if both A and B are rational. Yeah, so at this point we could do a demo, but let's save that for the actual talk on Thursday. Right, so we're going to make some more definitions. So we have notions of inverses for tangles, which we're going to define. So here's another definition. So if B is a rational tangle, then we define minus B, or B star, as the mirror image. This is the of B. And so this is done by reversing all the crossings. So let's say if we had this, then we reverse this to something that looks like this instead. So we're reversing all the crossings. And now we have some more notions. We have what we'll refer to as the C inverse, so the clockwise inverse, which we will denote by as such. We could write it like this if we want to. So this is obtained by first rotating 90 degrees clockwise. Clockwise, so in the other direction. And then we take the mirror image. And similarly, we have the counterclockwise inverse, which which we'll denote by 1 cc over b. And this is the exact same thing, but in the other direction. So now we're rotating 90 degrees counterclockwise, and again, taking the mirror image. Okay, good. So now we have some algebraic structure on our tangles, and now we're going to refresh our memory on continued fractions, because there's an interesting connection between the two. So a bunch of you might have seen this, but a continued fraction is an expression of the form. So it's really what it sounds like. Maybe I can dry it off a bit more. So all of the a's here are integers. We got a plus 1 over a1 plus 1 over a2 plus 1 over, and so on. And we can stop if we want to. We don't need to. We also have the notion of infinite continued fractions, and we can write this as, so this is the notation we use, a naught, and then a semicolon, and then a1, a2, and so on. And then we close the bracket. So let's take an example. So the golden ratio is equal to the continued fraction, which is given by an infinite sequence of ones. Right? And this is not difficult to see. We can write it as follows. I mean, we could just consider this expression 1 plus 1 over this. And yeah, the golden ratio satisfies this. Another example is the following. So we can approximate rational numbers or also irrational numbers very well by continued fractions. And in a precise sense that maybe you've heard of it, it gives you the best approximation. So for example, pi is written as a continued fraction as follows. So there's no sort of clear pattern here, but I'm going to write down the first few entries. And if we truncate this at certain points, we get approximations. So for example, we get the approximation 3. So any engineer would tell you this. We also get 3 plus 1 over 7, which is 22/7. Or you can also go even further. You could take 3 plus 1 over 7 plus 1 over 15. And this gives you 333 divided by 106. And this is also an excellent approximation of pi. Right. And so now back to continued fractions. So back to rational tangles. It turns out for rational tangles we can associate to every rational tangle a continued fraction, which will give you a rational number, and this is quite interesting. So we'll see later that this is in fact a complete invariant for rational tangles. So just compute this number and it will tell you which isotopy class you're in. So, for a horizontal tangle, that's obtained by applying, so we're starting with a zero tangle, and then we're applying obtained by, so TA1, and then we're applying TA2 prime, and then so on. So I'm not going to write it to the end because we sort of don't know if the AN which we end at is going to be a primed or a non-primed element. We associate to this the continued fraction AN semicolon, AN minus 1, and all the way down to A1. So remember, this is AN plus 1 over AN minus 1 plus 1 over, and then we stop at some point. So this is sort of in the reversed order of which you're applying to the zero tangle to get where you want to be, right? So we started by applying A1, and then we ended by applying TAN or T prime AN, and this appears as the first entry in our continued fraction. And similarly, so for a vertical tangle, which is obtained by, well, we need to start with T prime A1, and then we do TA2, and so on and so forth. Then we write something similar, but not quite the same. So in that case, we start with a 0, and then AN minus 1, and so on, all the way down to A1. Right. So in both cases, we get a fraction, so we can just compute this rational number, and we'll denote this as f of b, so the fraction of b. And so I'm going to tell you some basic properties of this fraction. So these aren't so hard to prove, so it's a good exercise. It's basically just unwinding the definitions. So proposition. So B is a basic tangle. And then we have the following. So the first property is that 1 over f of b is equal to f of 1 over b. And so here the division sign could be either a C division, or it could be a CC division, so the counterclockwise inverse or the clockwise inverse. This is the first one. The second one is if TA plus b, so added from the left in this case. So note that if we write TA, then this is not only a twist, like twisting strands A times, but it's also considered to be a tangle. So if I write TA, I mean the tangle that we get by starting from the zero tangle and then applying the move TA. So if this is also a basic tangle, then we have that f of TA plus b is equal to f of TA plus f of b, which is equal to yeah, so this is just A plus f of B. And then we have some more properties. We have two more properties. The third one is the following. So so f of minus TA, let me see if I can write this all down correctly, is equal to f of t minus a, which is equal to minus a, which is equal to minus f of TA. And we've also got, so for the primes, minus t prime a is equal to f of t prime minus a, which is f of 1 over t minus a, which is equal to minus 1 over a, which is equal to minus f of 1 over ta, which is equal to minus f of t prime a. I think this should be right, yeah. And so again, so these division signs, whenever they appear inside the fractions and are applied to tangles, we use either one of those. And so the final one, it's a bit shorter, is just stating that f of minus b is equal to minus f of b. Okay, so this is pretty much everything that we should need. And now we're going to connect everything. Unfortunately, the clock on the wall is not working, so I don't know how much time I've got left. So now we're going to talk about Conway's theorem. So Conway's theorem. Okay, so every rational tangle, as I said, is isotopic to a basic tangle. So I'm going to state the following theorem for basic tangles, but it's also true for rational tangles in general. And so the theorem says the following. So let T1 and T2 be basic tangles, basic rational tangles. And the theorem says that if the associated fractions are the same, then T1 is ambient, isotopic to T2. Okay, so this is maybe quite a surprising theorem. And to prove this, we're first going to need another theorem, which is called the flip theorem. And this says that a 180-degree rotation of a tangle, of a rational tangle, be in either the horizontal or vertical axis is ambient, isotopic to B. So I'm not going to prove this, but the idea is basically that we do induction over the number of twists. And yeah, the vertical case is a bit easier. The horizontal case is a bit easier. The vertical case is also not too hard. But it's an inductive argument, and that's good to know. All right. And now we're going to need the following formula. So, fact. So, A minus 1 over B is a minus 1 plus 1 over 1 plus 1 over b minus 1. Okay, this is just elementary school maths. You can prove it if you like. And so using this, we're going to prove Conway's theorem. Putting all the pieces back together. And so the idea is basically this. We're gonna start by considering two basic rational tangles, and then they're gonna have their respective continued fractions. These are rational numbers. If these are the same, then we're gonna convert these continued fractions to identical continued fractions, so the same sort of expansion, right? Using this formula. And then after doing this algebraically, like this is a unique thing that it could result in. I'll explain it in a second. And then we're going to mirror this topologically, and we're going to see that in every step we have an ambient isotopy. Yes. Right, so this is the idea. So the proof. So idea. Factor the ambient isotopy through it's called a regular tangle. The reason it's called a regular tangle is because it factors through a regular fraction. And what is a regular fraction? Well, so let's say we have a continued fraction, which evaluates to p over q. Then the point is that we can always write this as a continued fraction where only the first integer part is possibly negative, yeah? So we're going to write it in a way such that the ai are greater than 0 for all i's going from 1 up to n minus 1. So remember, the nth number was the first one that appeared in the fraction. So yeah, so we're going to show that we can do this algebraically, and then we're going to mirror it topologically. So we're going to use Lagrange's formula. And then first of all, well, I think it's easier if we just consider an example, and you'll see the principle. So we consider the continued fraction 3 minus 1 minus 1, 2. We can write this out as 3 plus 1 over minus 1 plus 1 over minus 1 plus 1 over 2. So first of all, we're going to bring all of the negative signs to the numerator. And so this is equal to 3 minus 1 over 1 plus 1 over 1 minus a half. And now we're going to sort of, going from the bottom to the top, we're going to apply Lagrange's formula. So this is Lagrange's formula. And then we're going to push all the negative signs to the front. So we're going to apply this to whatever we see here. Now we're going to get 3 minus, so 1 over 1 plus 1 over, so first of all, this a becomes an a minus 1, so that's going to be 0. And then plus 1 divided by 1 plus 1 over 1. Right, so the b is 2 in this case, so we're going to have 1 divided by 1 plus 1 over 2 minus 1. So we should get this that I've written down here. Now we simplify. Now this is a half, and so we get 3 minus, is this right? Yeah, so we get 3 minus 1 over 3. And now we apply Lagrange's formula a second time, so you can check the details. 2 plus 1 over 1 plus a half. So we can write this as 2, 1, 2. So in this case, we didn't need any negative signs, but the only thing we could possibly end up with that contains a negative sign will be contained in this first entry. Okay, so we can do this algebraically. Now, how do we express this formula topologically? Now, I've got a picture, so let me maybe try to draw this on the board. Testing my drawing skills. Okay. So we first going to construct the B part, like the second part of Lagrange's formula, and then we're going to piece it together. So we start with a tangle B. Now we can apply a twist. A negative twist, so this is going to be B minus 1. And now we take the clockwise inverse. So we take this clockwise and take the mirror image. Okay? So this is now we add 1 to this from the left. So we'll get something that looks like this. Let me see if I can draw this. This is still B inverse. This is just 1 plus 1 over B minus 1, right? So now we're going to take the counterclockwise inverse. We get 1 over 1 plus 1 over B minus 1. Cool. So maybe I'll do a couple more steps here. So it's not too much more to be done. And so this, and so the point is that we can pull this strand over to the other side. Now we get a much simpler picture, which, so now we're doing ambient isotopies. So we get something that looks like this. And now we, and now we rotate this. So we'll get something that looks like this now. So B will be rotated like this. Now these strands will have been resolved, but we'll still get a crossing here. And so this is equal to 1 divided by 1 plus 1 over b minus 1. This is what we saw with the c's here in the double c. Yeah, so this is nice. And this is the first part of Lagrange's formula. So let me sort of explain the rest. Now the rest is really simple. So we already had this, and so everything we need to add now is just, so we want to add a plus minus 1 to the left of this. Right. And now, if we do this, we get a picture that looks like this. So a tangle A here, and now we're adding a negative crossing as such. Now we paste this together with a picture from B, with a picture on the board right there, and we get something that looks like this. B. Now we can pull this strand over here, and we get a picture that looks very nice and simple again. And now this is this part. So we see we've just twisted this counterclockwise without taking any inverse. So this is in fact equal to, yeah, so this is the tangle A plus 1 over minus B. Because first we're taking the mirror image, then we're rotating counterclockwise, and then we're taking the mirror image again because we don't have any star here, we don't have any mirror image. And so what we've just seen is that on the level of rational tangles, this formula by Lagrange tells you that, well, whatever we had here is precisely equal to A plus 1 over minus B. And so this is all we need. This means that we can mirror everything topologically, and this concludes the proof of Conway's theorem. Yes. And so now we're going to move on to the converse. So in fact, there's an even stronger result, because this is an if and only if. So two rational tangles are ambient isotopic if and only if their fractions are the same. So we also have the converse. Of Conway's theorem. And so T1, T2 are basic rational tangles, and if they are ambient isotopic, then their corresponding fractions will also be the same. Okay, so to prove this, we'll need a bit more theory. So we're going to define a useful invariant for this. And so we're going to talk about the conductance invariant and the bracket. So I think the conductance invariant is something that comes from some like electro theory course, or like from electricity, so as in conductance of circuits, but it's useful here. And so we'll define, so we want some invariant conductance of T. In fact, we'll define this for not only rational tangles, but for all tangles, and we'll sort of specialize to see how this plays out for rational tangles. And so we want it with the following properties. So first of all, we want it to be an invariant. So if T is ambient isotopic to S, then the conductance of T is equal to the conductance of S. And secondly, if T is rational, then C of T is equal to the fraction of T. And we'll get both of these properties. But first I need to tell you what the conductance is. And so, so this is enough to prove the converse of Conway's theorem. We just need to prove that such an invariant exists. And so we can define this C using the Kaufmann bracket. So this is from like a standard knot theory thing that you do. You have a knot or a link diagram, and then you can compute the Kaufmann bracket. And so I'm not going to explain the Kaufmann bracket, but there are plenty of good references online that you can look at if you'd like. So first of all, well, when I'm using any sort of specific properties, I'll just spell them out. Well, so first of all, the Kaufmann bracket, it's not sort of well defined for tangles, but we can just do the normal expansions that we would do with a normal tangle. And at some point, if we have a tangle T and symbolically compute the bracket, we'll get an expression like this. So we'll get some polynomial in A as a standard for the Kaufmann bracket. And then we'll get these expressions, like formally the Kaufmann bracket of, so this should be the infinity tangle, and this is the zero tangle. So first of all, well, these aren't numbers. These aren't numbers or polynomials or anything. These are just symbolic expressions. And so, well, we can prove the invariant of the Kaufmann bracket under the second and the third Reidemeister move. So this is fine. The issue is the first Reidemeister move. And so we can't simply use this because it's not an invariant of the Reidemeister move. So we'll need to define something else. And so now what we're going to define is we're going to consider a specific ratio. So we're going to define this as RT of A. So this is a rational expression of polynomials in A. And we're just going to divide alpha t by beta t. Cool. So is this an invariant under the Reidemeister moves? In fact, it is, but we need to check the first Reidemeister move. And so maybe theorem. So RTA is invariant under R1 to R3, so the Reidemeister moves, or if you will, under ambient isotopy. So this is equivalent. And this is not particularly difficult to see. So when we apply the first Reidemeister move, then what happens is that the polynomial, the Kaufmann bracket of t is multiplied by either. So it's multiplied by either minus a3 or minus a to the minus 3. So this is the factor that sort of gets carried over. And the point here is that, so this depends if we're doing this Reidemeister move, if we're resolving this, or if we're resolving the crossing, that is, the other one. So depending on which is the overstrand or which is the understrand, we're going to get a minus a cubed or minus a to the minus 3. And the point here is that if we symbolically compute this on a tangle, then all of these factors get carried over in a similar way to both alpha of t and beta of t. So let's do a bit of an instructive example. So here's a formal computation of a Kaufmann bracket. So A, and then this gets resolved as follows, plus B. So we just use B for A inverse. And then we have the Kaufmann bracket of this instead. And so what we see is that we have a loop that gets carried onto both components of the resolution here, but we see that when we apply the Reidemeister move, the first Reidemeister move to both of these, or if we apply the Reidemeister move to this one and then compute this expansion, then we're going to get the same thing. So I don't remember if it's minus a cubed or minus a to the minus 3, but we're going to get the same factor in all of the places. And so this is the idea. And so this shows that this is, in fact, an invariant, as claimed. Right, so we got the first property of C that we wanted. Well, we haven't defined C, but so this ratio is certainly invariant under ambient isotopy. And so now we need to we're gonna specialize RT by evaluating it at a certain point and then multiplying it by some numbers. This is not changing invariance in any way. And then we'll get our desired result. So let's do this. I'm now going to tell you what CT actually is. Okay, so now I'm going to define CT. CT. So, well, this needs to be some number, right? And hopefully it's going to be rational if we evaluate it on rational tangles. So minus I being the imaginary unit, RT, and in place of A, we put the square root of I. Again, imaginary unit. Right, so property 1 is already satisfied, so we know that this is an invariant. Now we just need to show that it evaluates, well, for rational tangles, we need to show that this is in fact the same thing as the fraction of the tangle. Yeah, so first, so proof of 2. So first, compute C on the generating tangles. So this is just T1. and minus 1, and this is t minus 1. And then we're going to prove some properties of CT, namely that, so I'm lining out the strategy first, namely that C of t plus s is equal to C of t plus C of s. So this property we also have for tangles, so for rational tangles and the fraction of those, so this is good. And in fact, this is all we need to do, because, so first of all, note that this is also equal to t prime of 1 and t prime minus 1. And now, so, well, it makes sense that, okay, we have the horizontal addition, but do we actually have the vertical addition as well? And yes, we actually do, because if we consider the plus prime operation, then we can express it as 1 C inverse of 1 CC inverse of B plus 1, this generating tangle. This is equal to B plus prime of, well, minus 1. And of course we can just, slap these together, just concatenate a bunch of minus 1 vertical tangles to get any vertical tangle. So everything we can do with a plus addition is we can do with a plus prime addition. So we can realize the plus prime operation by using the plus operation and the C and CC inverses. And so yeah, so let's start by computing C of the first generating tangle and see that it agrees with a fraction that we would compute. Right, so we need to compute this. So first of all, we expand brackets, and then we get the following. So A, this is just simply doing, because, yeah, I mean, this tangle is just this. So we just have one crossing, and then we resolve it using the properties of the Kaufman bracket, and we get down to the infinity and 0 tangles immediately. And then we would have the following expression. So B, again, placeholder for A inverse. And here we got the 0 tangle. This is nice. And so now we just use our definition of CT. And now we get that C of the generating tangle is just equal to, well, we had a minus I first that we needed to multiply everything with. And then we had this ratio. And the ratio, well, first of all, we have a polynomial in A, and we evaluated at the square root of I. And so this is divided by A inverse evaluated at square root of I. So we get this, flip it, so we get minus I times I, and this is just 1. And this is the exact same thing as we would get by the fraction. So this is just one horizontal tangle. So we just get 1 plus nothing else. So this is fine, and we can do the exact same thing for the inverse of this. So we could do the exact same thing for minus 1, and we would get minus 1 in that case. And now we only got the final part. And so, in fact, showing this is not particularly difficult. I mean, probably coming up with it was quite difficult. But the proof is easy, right? And so suppose that T is a rational tangle that has the following bracket expansion. So eventually we get down to A infinity plus B 0 tangle And then we also suppose that we have a rational tangle S. Well, I mean, it doesn't need to be rational. The theorem would still apply, but yeah, I digress. Now, we have other integer coefficients. So C, we don't want to use the same again, plus D, 0. Now, the claim is that the bracket expansion of T plus S is equal to AD plus BC infinity tangle plus BD, the zero tangle. And now, if we compute this ratio, note that we'd get AD plus BC divided by BD. So we can split this up and cancel some stuff. Now, in the first part, D would cancel with D, so we would get A divided by B, plus in the second part, where B would cancel with B, we would get C divided by D. So this ratio is what splits like this. So this shows that as long as we're able to prove this claim, then we can in fact prove property 2. And now we're gonna, so this is the final part, we're just going to consider a diagrammatic calculation of this. So hopefully I can fit it all in one board. Yeah. Yeah, so we're going to write as follows. So T plus S is equal to, well, it's going to look like this. Here we got the tangle T. Here we got the tangle S. This is just our tangle addition. Now, what we're going to do is we're going to start by resolving T. So we apply the properties of the Kaufmann bracket only to the left part of this diagram for all the T's, well, for everything involved on the left-hand side, and we leave S untouched. And by assumption, this is going to bring us, this is going to result in the following. So A is the coefficient for the infinity tangles. So when everything has been resolved, this is what we're going to have on the left side, and S is going to remain untouched, plus B of this. So all of the zero tangles are going to carry over to something like this. Now this is good. Yeah, so now let's continue and just do the resolutions, or like the computations on the S parts of these diagrams and see what we get. So A stays, and then we're going to open up a big bracket. First of all, well, C is the coefficient for the horizontal resolutions of S. So these are going to become connected, and so we'll get this strand is untouched. Then we're going to get a loop, and then this strand is going to pop out. Plus D. Well, the other thing that can happen is we end up with something like this, and now we close our bracket. Okay, very good. And now plus B big bracket, C. And now, so we started by applying this to this first component. Now we apply it to the second component, and then we get something slightly different. So the infinity parts connects those again, and we get something that looks like this, which is just an infinity tangle. And then we add D to the other thing that can pop out, and what we get then looks like this. And then we close the bracket. Okay? And now we're basically done. So here we've got the infinity tangle, here we got the zero tangle, and here we got the infinity tangle again. Now, this is right? Yes, this is correct. Now here we've got something a little bit different. And so we have the infinity tangle, but we also have a loop. And now we know by the Kaufman bracket that if we take, so let's use this final board space to explain this, we have that if we have a disjoint union of the unknot and a knot or a link K, then we get this delta K. And now the delta is given as minus a squared minus a to the minus 2. And so now we're sort of stuck, but we've chosen also a specialization here for a. So in particular, a is the square root of I. And so if we evaluate this, we get minus square root of I squared, which is I, minus square root of I to the minus 2. So this is 1 over I. And so we multiply this by I again. And so here we get another negative sign which cancels this one. And so we get minus I plus I, which is 0. So this whole component just vanishes. Now, if we just collect the terms, we see that, well, for the 0 term, we get D times B, which is exactly what we should get. And for the infinity term, we get BC plus AD. BC plus AD. So this is exactly what we had. And so this concludes the proof. And yeah. So in conclusion, the fraction of a tangle, which we get by just writing out a continued fraction and then evaluating it to get a rational number, is a complete invariant for rational tangles.